All right, welcome to Unit 5, Lesson 2 homework help. The title of this homework is Pet Sitters. Okay, perfect. So we're going to start with number 1. Solve the following systems by graphing. Check the solution by evaluating both equations at the point of intersection. So solve by graphing means we are going to be graphing them. Let's do two different colors. Let's do purple for the first and green for the second. All right, so purple for the first. Let's get some points up here that we know are going to be on the graph. So y equals, oh, hang on, that's not what I meant to do. Sorry, moving over a little bit. There we go. Y equals 3x minus 2. So our y-intercept is going to be -2. That should be right here. And then 3x means if we go over 1, to the right 1 and up 3. So that'll be another point, that'll be another point, that'll be another point, and so on. All right, so we've got some points drawn on here so far. And that one. All right, there we go. So those are some points, and now we can go back a little bit smaller and draw these. Right. That seems to be a pretty good approximation for that. And now let's go in green on the second equation, and let's figure out what we're doing here. Y equals x. Oh, y equals x is easy, right? That's the one that just goes up at a diagonal like this. And some of these points might not be perfectly on, but that's okay. I think we've added enough. I think that's probably going to be enough. All right, so let's go back, drop it down, and right, let's see. That looks pretty good. Okay, so that's a lot more points than you need to draw, but that's fine. You are more than welcome to draw every single point or just enough. So it says, so we've graphed them. Check the solution by eval. All right, so it looks like the point of intersection, if we zoom in here, it should be this point right here. Let's make this one orange. Right, that is definitely our point of intersection, and that point is the point 1, 1. All right, so we're going to check if that point 1, 1 satisfies both equations. So, all right, so if we plug in to the first equation, we'll do this one in purple. Oh, there we go, we're already in purple. 1, 1 means, well, right, so x equals 1 and y equals 1. This is what we're assuming. So the first equation would say that 1, the y, is equal to 3 times the 1x minus 2. Right? So 1 equals 3 times 1 is just 3 minus 2. Yep, 3 minus 2 is 1, so 1 equals 1. That works. And then our second equation, we'll do this one in green. Y equals x. All right, so y, which is 1, is equal to x, which is also 1. Yes, that checks. All right, so this first one is all set, and we'll move on to the next one. Oh, we're going to skip over number 2 for right now. On to 3, which is on the next page. And we're going to do the same process, maybe a little bit faster this time. So y equals x plus 3. We'll do this one in purple. Y equals x plus 3. Let's get some points a little bit bigger. All right, y equals x plus 3 means our intercept is 3, and it proceeds up at an angle like this, right? Right, it proceeds up with a slope of 1, right? Because if it just is y equals x, that's a slope of 1. All right, so that should be enough points for the first one. We'll connect it later. And then we'll go with the second equation, which we're going to do in green. Y equals -2x plus 3. All right, so our intercept is still plus 3, but we're going down 2 as we go to the right. All right, -2. So there we go. All right, this should be enough points now, and we'll just adjust this back to a thickness of 1. Right, that looks pretty good, and we'll go back to a line thickness of 1 here. That looks fine. All right, and it looks like our intersection point once again is right here, which was actually our intercept for both, and that is the point 0, right? X equals 0, so 0, 3. So now let's figure out if that actually works for both equations. So we are going with, we'll keep this in orange, x equals 0, y equals 3. X equals 0, y equals 3. That's what we're checking to see if that creates true statements for both equations, if that makes them both true. So y equals x plus 3. Y equals x plus 3. Right, y is 3, so 3, we'll put this in parentheses, equals x, which is 0, plus 3. Right, which is just 3 equals 3, and that is correct. That's true. And then the other equation, y equals negative 2x plus 3. Negative 2x plus 3. Our y is 3 equals negative 2 times x, which is 0, plus 3. 3 will become a 3, equals, negative 2 times 0 is just a 0, so 0 plus 3. And this is just 3 equals 3. So that checks as well. So our solution to this second point, or the second problem, which we'll write, I guess, in purple, is 0, 3. Wow, it really didn't like that one. There we go. 0, 3. That was our solution for the second one. All right, and question 4, we're doing this one more time. So let's get started with our points. We'll go up to 3. Maybe we'll do the first one in purple. Y equals 3x minus 8. So right off the bat, we're going to go to minus 8 and put a point. Missed it by a little bit. That's okay. Right? There we go, minus 8. And now a slope of 3 means we're going over to the right 1 and up 3. So that's 3 and 3 and another 3. And that should be good. Maybe we'll do 1 down to the left. Perfect. And then we'll go over and see, let's see what we can get for a trace on this. If we hold down, it should straighten out for us. Excellent. Perfect. All right, so that's our first line. And then our second, we're going to go to y equals negative x. So we're going to, we don't have a plus value, which means it goes through the origin. All right, so that's not quite through the origin. Here we go. Let's get through the origin on this one. There we go. That's a good dot. Negative x means it goes, as it goes to the right 1, it goes down 1, right? It's y equals negative 1x, right? So here we go, going down this way. And we'll also proceed up and to the left. That's fine, right? So continuing the pattern. Excellent. And now let's make sure, right, that there is our line, and it looks very clearly like the intersection point happens right there. Right? Now, what is that point? What is that point? It looks like it's at 2, negative 2. That's what it looks like to me. So let's write 2, didn't like that, 2, negative 2, right? It's 2 to the right and then 2 down. So 2, negative 2. So we are going to go and check and see if this point works, right? 2, we're not writing it as a point up here. We already have it written as a point. X equals 2, y equals negative 2, right? That's what we're checking. So let's switch back to purple. All right, first equation is the purple equation, y equals 3x minus 8. So y equals 3x minus 8. Okay, what we're going to do first is make our value, right? We're going to input the values we think are the solution. So let's go with y is y is -2. Oh, didn't quite happen correctly. Y is -2, and then equals 3 times x, which is 2, minus 8. All right, and now we are simplifying. All right, so -2 equals, what's 3 times 2? It's 6. 6 minus 8. All right, what is 6 minus 8? It is -2, so -2 equals -2. All right, that is a check, which means this point is actually on the line as we expected. And now let's check our other equation. We have y equals -x. Y equals -x. So remember, our y is -2, so -2 equals negative, and then x is 2, right? So this becomes -2 equals -2. And that is correct. So we are all set with our solution here. Oh, zoom back in so we can write it. Our solution here is 2, -2. 2, -2. And we will move on to the next problem. Okay, set. Looks like we have our own instructions here. This is good. All right, the Utah Jazz scored 102 points in a recent game. The team scored some 3-point shots, some 2-point shots, and many free throws worth 1 point each. Find 5 combinations of baskets that would add up to 102 points. Clearly state how many of each type of shot was made during the game to produce the team's score. Okay, we can do that. So, first off, let's define some variables. All right, so let's call our 3-pointers. We'll call our 3-pointers. 3-pointers, we'll go with like triple. So like 3 would be like a triple, like triple point. So T equals 3-pointers, right? D, or a double, equals 2 points, right? The number of 2 points. And let's go with M. We're gonna go, yeah, we'll go with M. Or, oh wait, actually, let's go with F for free throws, right? F equals the free throws, which are the 1-pointers, right? So 1 point. 1 point, that one has to be singular. And, all right, there we go. So T, D, and F. So if the number of 3-pointers, T, so the total of the points needs to be 102. So we would say that you get 3 points for each T, 3 points for each T, plus 2 points for each D, right, for each double point score, and then 1 point for each F, so just plus F equals 102. Right, so there's our equation. That's an equation that's going to work. But now we have to figure out 5 combinations of baskets that would add up to 102. And it does say that the team scored some 3-point, some 2-point, and many free throws. So we can't just say 102 of the free throws and no other points, because the question says they scored at least some of all 3. So we can't have zeros for any. So let's say they scored 10 3-point shots. 10 3-point shots. All right. So if they had, let's make a little table here. turned off on me. Hang on. Turn back on. It's motion activated. So it's when I'm standing at the board that it sometimes it turns off if I'm not like moving back and forth enough. So here we go. If we have a table here, right, of our 3-pointers made, our 2-pointers made, and our free throws made. And let's have total points over here. Right? And our total points will be over there. So if they, let's say, made 10 3-pointers, that would be worth 30 points, right? And we'll put it in parentheses, right? So if they made 10 3-pointers, there we go. If they made 10 3-pointers, that would be worth 30. If they made, I don't know, let's go with 20 2-point shots or 20 double-point shots, that would be worth 40 points. Right? And how many free throws would they have to make in order? How many free throws would they have to make? Well, they'd be at 30 from the 3-pointers and 40 from the 2-pointers. So 30 plus 40 is 70. They would need another 32. Right? They need another 32. So that's one combination that would work. 10 threes, 22s, and 32 free throws. That could work. What if we up the threes? What if they made 20 3-pointers? Right? That would be worth 60 points. And maybe they still, not quite. Right? That would be worth 60 points. And maybe they still made 20 2-pointers. That would be worth 40 points. And now they only made 2 free throws. Right? 60 plus 40 plus 2 is 102. So that would work. And there are going to be a lot of potential solutions, right? You could pick nearly any number from 1 to probably 30 or so for the T's. For the D's, right, you could probably come up with some combination that has anywhere from 1 to 45 or so. Right, so there's going to be a lot of variation for that. And then free throws, I mean, that's just going to be sort of like filling in the blanks from the 2s and the 3s. So, but they're going to be a lot. But let's see, how else are we going to do this? Let's go with, what if they scored 30? What if they scored 30 3-pointers? That'd be worth 90 points. That's a lot. And then maybe they scored 5 of these 2-pointers. That's worth 10 points. And then they only scored 2 free throws. That would be 102 points. So let's find out another 2. All right, maybe this is too many 3-point shots. Maybe they only scored 5. Oh, hang on. We need space for there to be 5 of these rows, and we only have 4 rows right now. So maybe they scored 5 3-pointers, and that's worth 15. Maybe they scored 40 2-point shots, and that's worth 80. So we have 15 plus 80 is 95, so they would have to score 7 free throws in order to reach 102. Okay? And last but not least, let's go back to maybe 10. I feel like 10 was a good number, right? 10, so they get 30 points on on 3-point shots, on triple point shots. Then in the 2 points, for 2 points, what if they scored 30? What if they scored 30 of them? Right, that would be worth 60 points. And then, right, we'd be at 90, and they'd have to score 12 free throws in order to be at 102. Right? So all of these combinations will work, right? If we go and scroll and we look over here, right? All of these combinations would work. And if we had a graph right? If we had a graph that shows 3 different variables, this would be a 3-dimensional graph. We could actually say that all of the different like point values, right, would be 102 with 3 variables graphed, right? So that's kind of interesting. But it's easier in a table to see. Like if you score 10 3-pointers, you could either get 22 points and then 32 free throws, or you could do 30 free throws and 32 pointers and only 12 free throws. So there are a lot of options, a lot of ways to make this happen. But I digress. Let's move on to the next page. All right, so we're right to the go. Graph each equation below, then determine if the point 3,5 is a solution to the equation. Find a point other than 3,5 that is a solution, and show that point on the graph. All right, so we are graphing the equations. Find a point. All right, figure out if 3,5 is a solution. Let's write down our sort of action items. All right, so we're graphing each. Oh, didn't love that. You know what? Let's use the highlighter. I don't know how this is going to go. All right, that's fine. Kind of like that. Let's zoom in a little bit. All right, so graph each. Oh, come on. I got this. Here we go. All right, graph each equation below, then determine if the point is a solution to the equation. Okay. Find a point other than 3,5. All right, so find a point other than 3,5 and show it on the graph. All right, so we're doing 4 things. And our first equation is y equals 2x minus 1. And look at that, I have it up here, y equals 2x minus 1. Let's recall that I gotta go check. It was the point 3,5, yes, okay, good. I was about to write it down, I wanted to make sure it was 3,5 and not 5,3. So the point that we need to check each time is 3,5, right? 3,5 is the one that we're checking each time. All right, so y equals 2x minus 1. 2x minus 1 means we're crossing at the minus 1, right? Our y-intercept is going to be minus 1. 2x just means we're going up like this. There we go. All right, this is our pattern. Done. All right, let's go back. And we graph it. There we go. So we've graphed it. Now let's figure out, is the point, right, and we'll do this in purple, is the point 3,5 on the graph? Well, where is the point 3,5? 3 would be, let's do this on a little bit smaller. 3 would be here, 5 would be here, which means this is the point 3, 5. All right, so it is on the graph, right? So 3, 5 is on the graph. It is. And now we have to find another point that's on the graph. Well, we said that our y-intercept, right? We said that our y-intercept was this point, right? So what is that point? That's the point -1. Sorry, not -1. Our y-intercept is always x equals 0, so 0, comma, -1. All right, so maybe we'll write down a little summary. 3,5 is a solution. And 0, 1, sorry, 0, -1 is also on the graph, or is also a solution. All right, and it didn't ask us to do so algebraically, I don't think. Yep, it didn't ask us to do it algebraically, but we could have also algebraically shown that 3, 5 is a solution by plugging in 3 for x and 5 for y. We could have done that. Same thing we could have done for 0, 1, but we don't need to do that because it didn't ask us to. All right, so 9, here we go. let's first remind ourselves we are looking to see if, right, 3 comma 5 is a solution. And we'll put that 3 comma 5, we'll just start off right now. That's 3, that's 5, so 3 comma 5 is this point right here. And now let's plot the equation. Let's plot this line and see if that point is one of them. So 1/3 x plus 2, all right, so plus 2, we're going to there. And then 1/3 x means we're going to go up 1 over 3. So up 1 over 3 is there, 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 and there. Here we go. And now we'll go down to the left just a little bit to there, all the way to the edge. Okay, so that is our, that's our line. We'll get it plotted. Perfect. And it does not look like the point, right? It does not look like 3, 5 is on that, is on the line, right? It is not on. But what is another equation or another point that is? Well, it looks like our intercept right there. Oh, wow. All right, so if you have the arrows still on, it draws really weirdly. There we go. This point is definitely a solution, and so is this point. We can actually, we'll write both in case you wanted to do either one. So our intercept is 0, 2. And this other point that was on the graph we said was 3, and it doesn't look like it's all the way to 3, 5. It looks like it's only at 3, 3. So let's write this now. 3, 5 is not a solution. Is not a solution. 0, 2. And 3, 3 are solutions. All right, so that's how we would solve number 9. Let's move on to the next one. Oh, did we have to do number 10? Nope, didn't have to do number 10 or 11, so we're skipping past. Aha, number 12, and it looks like the instructions are going to be down here. All right, the tables shown represent different arithmetic sequences. All right, back to sequences. We've done these though. Arithmetic sequences. Fill in the missing numbers, then write the explicit equation for each. Ooh, okay. So we also need to write the explicit equation. We can do that. Explicit equations they're just the things that we've been working with the whole time, where it's like y equals something or x equals something, and it's only one equation by itself instead of, if you can recall, the recursive equations, right? Recursive form of sequence equations will give like the current value based on the previous value, and then it'll give some starting point in a separate equation. So explicit equations do that, but just by themselves, right? Just a single equation, not two equations. So arithmetic sequences. All right, so that means that we are doing addition or subtraction from each step to the next. All right, so if we're going from 17 all the way to -7, and it looks like, right, if this is a jump of 3, let's see, if this is a jump of 3, this is +3, and then we have to go 17 to -7, that's -24. So if we have to go in 3 terms, right, 3 steps, we have to go -24. That means each step needs to be, right, -8, I think, right? So this should be -8. Oh, this should be -8, and this should be -8, right? And let's check to make sure that makes sense, right? 17 minus 8 is 9. 9 minus 8 is 1, and 1 minus 8 is -7. Okay, so each step is minus 8. One moment. All right, we're back. All right, so we've filled in this one with 9 and with 1. Let's do the same thing here, but maybe a little bit more condensed. We're jumping, it looks like 12 steps. 12 steps to cover minus 4. So the net change is minus 24. That just doesn't look like a 4 at all, does it? Maybe it did. Minus 24. All right. So 12 steps to go minus 24. That means that each step needs to be minus 2. So a step needs to be minus 2. That looks like a little 2, doesn't it? Each step needs to be minus 2. So 17, and then 15, 13, 11, 9, 7, 5, 3, 1, negative 1, negative 3, negative 5, and that would make negative 7 our last one. Perfect. And then we didn't even need to do 13. It wasn't circled. I just went into autopilot. Okay, so number 14. And we've been skipping the equations. Hang on. We've been skipping the equation part. So write the explicit equation. Let's do that. Sorry, I'll do that in purple. We'll do it over to the right because, you know what? We'll do the equation part over here. All right, so f of n equals, and our starting term, like if we plug in 1, we have to get 17. So we should get, let's say we should get, and we're taking minus 8 each step. So it's going to be minus 8, right, which is the step value, times n minus 1 plus 17, because we're starting at 17, plus 17, right? So this means that when we plug in a 1, we should get minus 8 times 0 plus 17. If we plug in 2, we should get minus 8 times 1 plus 17, which would be 9. So this will work out, right? So this is our explicit equation. Sorry, I jumped ahead there. This is our equation in explicit form. All right, my mistake. Let's go down and do 14 because that's the one it actually prompted. Here we go. In green, we are jumping from 1 to 7, so we're doing 6 steps, right? 1, 2, 3, 4, 5, and 6. So 6 steps. Net change is still negative 24. So if we're doing 6 steps to go down 24, that means a step is minus 4. And let's fill that in. So from 17, we'd go to 13, 13 down to 9, 9 down to 5, 5 to negative 1. Oh, sorry, not negative 1. What am I talking about? 5 to positive 1. There we go. 1 to negative 3, and negative 3 to negative 7. So that works out. And now the equation. We'll do it in a different color again. F of n equals, our step is now negative 4, so minus 4 times n minus 1. Minus 4 times n minus 1, and our starting value plus 17. There we go. So that is our equation. All right, and now number 15. Each of the sequences in problems 12 to 14 begins and ends with the same number. Would the graph of each sequence represent the same line? Justify your thinking. Oh, well, no, definitely not, because our steps were different, right? If we look up here at just 12 and 14, because we were supposed to skip 13, right, number 12 had a step of -8, but number 14 had a step of -4. So no, right? Because the steps were much steeper, right? We were stepping down further when there were fewer steps to go down 24 in fewer steps. That was way steeper. So no, the slopes would be the same. Sorry, the slopes would be different. Would be different. We'll say decreasing. Decreasing by 24 in fewer steps means the steps means a steeper slope. Steeper slope. There we go. All right. A couple hiccups in this one, especially like doing some of number 13, but that is okay. We didn't write the equation, so that's fine. And that wraps up this homework.